Yeah, thank you, Sarah, and thank you, Sam, for chairing this talk. Thank you also to the ISA staff for the opportunity to speak today. And obviously, as a Davos student, it'd be remiss of me not to say thanks to Davos for all the hard work he's put into these. I think we can all agree it's been a great resource. It must be a very weird time for a lot of us. And I've seen sort of first-hand amount of effort and work that's gone into these. So thank you for that. So yeah, as Sarah said in the introduction, I recently completed my PhD project. We focused on technique of cardiac optical mapping, and a bit different to the talk we've just seen. My talk is going to focus on more technical aspects behind the technique of cardiac optical mapping, and I hope to give you some insights into the field, where it currently stands and where it's moving. So I realised that within the audience, there's probably a wide range of familiarities with the technique of optical mapping, so I thought I'd just give a brief introduction. So in this technique, we are interested in multicellular preparations. So these are things like ex vivo animal hearts, but we can also apply it to monolayers, cardiac slices, ventricular wedges, and so on. And what we do in optical mapping is we load fluorescent dyes that are sensitive to either transmembrane voltage or intracellular calcium concentrations. Then, by effectively illuminating these preparations and by appropriate optical setups, we can use high-speed, high-resolution cameras. So things like CCD or CMOS cameras are the most widely used. And thanks to these setups, we're in high detailed images of the cardiac electrophysiological behaviour of the heart or of our preparation. Once we process and analyse these data, we can get really detailed information. For example, here you can see in a mouse heart, activation sequences and action potential duration morphologies mapped across the whole ventricle in resolutions which just aren't possible with other techniques. And what this allows us to do is then use optical mapping to apply physiological experiments. For example, here I'm showing a very simple experiment where we have, again, a isolated mouse heart, which is loaded with a voltage-sensitive dye. And we've perfused into this mouse heart increasing concentrations of the sodium channel blocker flecainide up there, and then also gap junction uncoupler carbon oxide. As you can see, thanks to optical mapping, as we increase the concentrations of these compounds, we get the expected increase in the activation times, shown by the sort of crowding of the isocolor lines and the longer activation times in the maps here. And you can see that mapped by the group data here, showing the slow conduction velocity on the right. But what optical mapping allows us to do, crucially, is move beyond sort of these global changes and look at sort of specific spatial changes and where these occur. For example, this is a study that we were involved with James Winter, who at the time was down in King's College London. And what he was able to do was use optical mapping to look at Alternans behaviour, so this is the temporal changes in the cardiac, for example, active potential duration or calcium duration and so on. But what he was able to do, thanks to optical mapping, is to see also the spatial relationship of these phenomena. And what he was able to do, thanks to optical mapping, is see that you get the role discordant alternans have in the onset of ventricular fibrillation. On the right here, you can see what happens when you get discordant alternans. So you have areas of the heart which show a long action potential duration next to areas that show a short action potential duration. The result is crowding of the isochronal lines, which not the crowding of the repolarization times. This causes a functional conduction block, which then manifests in the next beat as a actual sort of slowing of the conduction velocity, which causes then conduction block and the onset of ventricular fibrillation. Further application of optical mapping, which has seen more and more use over the last few years, is combination of optical mapping techniques to map cardiac electrophysiology with optogenetics. So this is use of optins such as channel optin 2 and others to use light to actually modulate the cardiac properties. So this is an example of some work that we've done in collaboration with Ming Lei's group down at Oxford, where he has a mouse model which selectively expresses channel optin 2. So this is the light-sensitive, non-specific cation channel, which I'm sure many of you are familiar with. But it successfully expresses channel optin 2 in the left side of the heart, thanks to its expression underneath the promoter of a PNT enzyme. Thanks to optical mapping, what we can see is that in the intrinsic heart, so what you're looking at here is atrial perforations from these mice. So this is the left, right atrium here and left atrium. And the intrinsic pacing conditions, we see, as we'd expect, the conduction beginning in the sagittal atrium only towards the right of the atrium and spread back. However, when we move to optogenetic pacing, so we use blue light, we see that blue light excites the channel optin 2 in the left atrium first, and then we change the activation pattern. And thanks to optical mapping, we're able to see this in really high detail. Now, hopefully that's sort of giving you a brief insight to optical mapping and sort of why it might be a beneficial technique. However, it also has associated with a number of challenges. So we don't have time to go into details of all these today, so I've just briefly sort of listed a few and given some helpful references if you want to read these further. But I'll briefly just introduce a couple of these challenges and then focus on a couple at the end. So one of the problems with a traditional optical mapping setup with a single camera setup is that you're looking at one face of your cardiac perforation. This is problematic because it leaves large parts of the tissue unimaged, and it also can distort the complex 3D morphology of the cardiac perforation. But more and more, we're seeing increased utilization of multi-camera panoramic setups and wider availability of these technologies. Another sort of challenge of optical mapping is the actual intrinsic nature of using light to interrogate biological tissue. This can be in the form of side effects of fluorescent dyes, so people report things like conduction slowing when we have these fluorescent dyes and so on. Will also be actually the fact that obviously light will interact with the tissue. We get phenomena such as photon scattering and tissue integration, which can effectively almost blur optically recorded action potentials and can mask very subtle changes in, for example, action potential morphology. But the two areas I'm going to focus on today are some the fact that optical mapping requires motion uncouplers. So these are compounds, obviously often small chemical compounds, for example, blebistatin, which uncouple the actual contraction of the heart, which obviously reduces the physiological relevance of optical mapping experiments. And also the fact that for a number of reasons, including high resolution requirements, the low fractional changes in fluorescence outputs and so on, optical mapping signals can often be a lot lower quality than you might expect from electrotechnique, for example. Therefore, specific and quite extensive processing analysis is required. We're starting with motion couplers. Firstly, why are they needed? So here you can see an example of a mouse atrium, which we have optically mapped with fluorescent dye. However, what you can see is that we have superfused, in this case, the heart with a mechanical uncoupler on blebistatin. We can see in one area of the heart, marked in red, that this uncoupling has not occurred. You can see on the right then what this does to the recorded action potentials. Instead of getting the nice monophasic repolarization, as you might expect from a mouse atrium, you get sort of this second hump. And this is not physiological, or at least not physiological, so physiological behavior. This is not a fact. The fact that the tissue in this part of the heart is moving, therefore distorts our recorded signal, so we can't effectively measure repolarization dynamics in this tissue. Why is this important? Well, even though we need these compounds most of the time to perform optical mapping experiments, it's been previously shown and been continued to be shown since that these compounds fundamentally change the physiological behavior of the heart. This could be through releasing the metabolic demand or just sort of physiologically changing the condition of the heart. So thankfully, over the last few years, there's been a number of work looking at ways to perform optical mapping in the freely being heart. And what I'm going to show you here is just an example from one very recent study from the previous week or so from a group down in Göttingen who've done some really great work in this area. And there are many other studies which also do this. But what they've done is combined ratiometric imaging, so this is dual excitation imaging, with sophisticated computer vision motion tracking techniques to allow optical mapping in a freely being heart. The results, as you can see here, is that they can record action potentials that do not have this characteristic distortion due to the failure of mechanical uncoupling to record optical action potentials. And what you can see is that when they're able to do the optical mapping experiments in the freely beating heart, we get fundamentally different results. First, in both action potential duration, as seen at the top here, but also in the dynamics of arrhythmia, in this case, in ventricular fibrillation. And finally, what I'm going to focus on the last part of my talk is that what I mentioned before, that fact that we need high resolution, both spatially and temporally, coupled with factors such as low fractional change, means that the optical mapping signals we can record in raw form are often very noisy. This requires significant processing analysis to again get effective parameter quantification at the end. For example, here we're mapping 8D50. For this reason, my PhD project actually focused on producing software for analysis of optical mapping data, and this was all published early last year, so I won't go into too much detail about this, but we designed and published a software for analysis of optical mapping data, and others have done similar. And hopefully what these tools will now allow us to do is to broaden optical mapping analysis so anyone who has the hardware capabilities will easily be able to analyze this software. And you can see there some links to the software if you'd like to use it for any of your data. But what I'm focused on at the moment is trying to see if we can sort of reframe how we actually analyze these optical mapping analysis by making use of more novel computational techniques. Here is one example where I've looked at the use of machine learning for optical mapping analysis. So what I have done is try to, instead of, for example, mapping APD 50 or conduction velocity or any sort of traditional parameters we measure. Can we use machine learning techniques to sort of reframe the questions? Instead of looking at, say, has this part of tissue changes APD or CV or so on, is this signal corrupted by noise or artifacts? So can we use machine learning to see what signals can be analysed? And then can we look at use machine learning to see, for example, has this tissue been exposed to a drug or is this tissue disease? So we map, instead of climate changes, actual physiological changes. So to test whether this is possible, I took again optical mapping experiments where we fused sodium channel blocker flecainide at varying concentrations. I then used these data to train a machine learning algorithm. In this case, it was the neural network based on the LSTM architecture. Basically, and then trained an algorithm to see, right, when I give it as another heart, which it hasn't seen, in this case the fourth heart, how well can the algorithm pick out the changes induced by flecainide. And you can see here that even though the fourth heart has not been seen by this algorithm at any point, we get reasonable responses in terms of our machine learning algorithm automatically from the actual potential waveform and no other information, picking out exactly how much flecainide this part of the tissue has been exposed to. Obviously, it's still very much work in progress, and others are also working in some areas, but hopefully this shows you where machine learning may be able to advance optical map analysis in the future. So finally, just to conclude, hopefully if you aren't familiar with the technique of optical mapping, hopefully I've just given you a brief overview of exactly what the technique and why it might be useful for studying electrophysiological behaviour at resolutions that are not possible with techniques. I've also briefly talked about some of the challenges with optical mapping, but hopefully I've shown you that the previous and continued advances in the field are overcoming these issues, and they're really making possible really innovative experiments that will hopefully further expand the use of optical mapping within the field. Finally, I'd say thank you to everyone at the Institute of Cardiovascular Sciences that I work with day in, day out, in particular the people on the noted down left, and also the collaborators down in University of Oxford for the optogenetic study. And also finally to thank the funders, in particular the EPSRC, who funded my PhD project. Thank you.
Okay, so I would like to thank all the three speakers to finish our session on time. First, thanks to Kutuba, then Zhao, and then finally Chris. Let's start our question answer session. The first question is from Helen Collins for Kutuba. So she's wondering whether did Kutuba notice any sex differences in terms of insulin treatment or TAC or targeting AKT in Kutuba's experiment, or these are data pulled, whether Kutuba used male and female mice together to generate these data.
Yeah, so thank you, Helen. It's a really important question. I'm sorry I didn't have time to.
So sorry to interrupt you, Kutuba, but I think your camera is switched off.
Oh.
So you may want to, there we go.
Yeah, I'm sorry, I was on the phone.
Sorry.
Sorry for that. Yeah, excellent question. So the main reason that we started the first series of experiment to use male and female is to look if there's any significant differences between the male and female in either the cardiac energy metabolism in general, namely glucose oxidation and fatty acid oxidation. And by comparing the data, we didn't see much of a difference between male and female in terms of the translocation of these kinases into the mitochondria. So we can see the same pattern of translocation with male and female. Also, there was no significant difference between cardiac energy metabolism in terms of glucose and fatty acid oxidation and glycolysis as well. So in the next, well, with the next series, we just decided to continue using both as far as they are both physiologically relevant and there's no significant difference. And then we pulled all the data together. So yeah, so the little secret here is started with male and female, thinking that there might be some differences, but no, after the experiments and analyzing data, we pulled them together. Yeah, good question.
Thank you. The next question I'm seeing is for you, Kutuba, as well. It says, were there any changes in GLUT4 due to altered AKT signaling?
Yeah, that's I think Joe Sun is asking about what is the site of action for the phosphorylated. If I'm understanding the question correctly, he's asking what is the site of action inside the mitochondria for the mitochondrial AKT. That's a really good and important question that we are trying now to find out. We reopened recently, so we're getting into that, and I would be happy to share that very, very soon. Yeah.
Thank you, Kutuba. The next question is from Viswani, and the question is whether you have noticed any kind of insulin receptor changes in your stress hearts.
Yeah, another good question. I'm really sorry, guys. We just finished this first series of our heart failure experiment just before the lockdown. So this is all in the process of the analysis. So hopefully we'll be able to tell very, very soon. But we're looking into that, absolutely.
Great. I think some of the questions I might see might be a little bit different. I'm trying to make sure that we're on the same page. The next question I see asks is aimed at Kutuba as well. It says, do you analyze for effects of the inhibitors on other classic insulin response pathways, including insulin-dependent glucose transporter GLUT4 in different studies?
Yeah, well, for the series of experiments that we did with the inhibitors, it was acute exposure, and we looked at the expression of GLUT4 and GLUT1 as well, and we didn't see much of a difference with any of the inhibitors. So yeah, we looked into that. We didn't see much of a difference.
I think the questions are a little bit jumbled. That's why it's not in order. I'm sorry. But this question is for Kutuba again, and it's from Eric Weatherford. And he's wondering whether you use separate antibodies for AKT1, 2, or you use the general AKT antibody. Yeah,
no, absolutely. Important question. So for the data that I showed, this is for AKT1 and AKT2. It wasn't specific, but what we're doing now is to go and see which AKT, whether it's AKT1 or AKT2, is actually more important in this, or maybe they are both important. So this is what we're doing right now. No, it's an important question.
Great. The next question that I'm seeing is for you, Kutuba, as well, from Gary Baxter, that asks, the attack model is a pressure overload model. Do you know if the role of AKT in stimulating glucose oxidation might be different in ischemic cardiomyopathy?
Yeah, so hi Gary. So Gary Baxter is my PhD mentor, and it's lovely to see him watching today. So yeah, so we haven't done any work with ischemic cardiomyopathy model, but what we know from experiment is that what we see, what this uncoupling between glycolysis and glucose oxidation exists in, for example, models of ischemia reperfusion during ischemia and during reperfusion, as well as we see as well in different models of diabetic cardiomyopathy. So I would speculate that maybe there is a good potential for this to happen in the ischemic cardiomyopathy as well. But good question.
Sorry, Kutuba, to give you shock. We did not plan this to give you no time to prepare your question, but it just happened. Anyway, the question I see the next is from Konstantinos, and again, it's for you. He's wondering whether the balance between phospho-AKT mediated effect of insulin versus release of fatty acids from the intracellular lipid stores.
Yeah, no. Hi, Constantino. How's it going? So, really good question. So what I can comment on is the effect of phospho-AKT and what it does to the glucose oxidation. I honestly not aware of the importance of this mechanism in deploying intracellular lipid store, or how it will act, or its role in deploying the lipid store in the heart. But I'm sure you know. So you probably can explain it a little, but I'm sorry, I don't know about the fact, but I can speak to the role of AKT in mediating the dark sensory stimulation or glucose oxidation.
Thank you. All right, the next question I'm seeing is for Dr. Wang. It says, as you mentioned, several groups, including our group, demonstrated the importance of O-GlutNAc in hypertrophy development under TAC or Ang2 treatment, inhibiting O-GlutNAc being sufficient to block hypertrophy development. However, we also showed that treatment with OGA inhibitors are excellent O-GlutNAc inducers, but are not sufficient alone to promote cardiac hypertrophy. What is your clue to reconcile these data in your nice paper?
First of all, I want to thank this question, and I'm very familiar with this paper, and we actually talk about in our lab meeting groups. Yes, indeed, but it's from our understanding is it's indeed a certain treatment that does not directly lead into hypertrophic growth. We also try to work on why. I think one of the explanations we have is the downstream events is not a general increase of gluconetic modification. It's rather certain players or key players being modified. So if you only look at the increase of gluconetic modification in all cardiac proteins, it may just shadow specific changes. I know it sounds like impossible to understand, but that's what we try to figure out, what particular protein be modified is not, and it's not just the general total increase of gluconetic modification. And I also want to point out is when we treat the carbon monoxide with gluconetic, we find different concentrations give different effects on cardiac hypertrophy growth. For example, we have a certain concentration, but two concentrations, they all increase gluconetic modification, was only one of those leading to hypertrophy growth. So I think, as I say, possibly due to selective change over specific proteins.
Okay, thank you. The next question is for Kutuba again. And this attendee is wondering whether you notice any kind of GLUT4 changes to your altered AKT signaling.
Yeah, good question. I think I already answered that question. We looked at the translocation of GLUT4 and the expression of it in the normal heart, and we didn't see much of a difference. In terms of heart failure, we haven't done that work yet, but it's a work in progress. So hopefully soon we will be able to tell. Yeah.
Thank you. I'm sorry, I think I dropped off for a minute on the Zoom call and it erased some of the questions on my end, but the next one I'm seeing is for Jiao Wang that says, congratulations on your work. How about inflammatory status in GFAT1 mice?
We did not measure the inflammatory markers in circulation, but we did was in the transgenic mice, in knockout mice, we did look at in the heart at protein at the mRNA levels of inflammatory markers. In the transgenic mice, we see the increase of certain biomarkers, and then in the knockout mice, there's a decrease. We didn't put it in the paper, but that's the findings we had. Thanks.
So the next comment is from Thomas, and then it's for Kutuba. So Thomas is wondering, how can you explain your recent data which suggest AKT enhancement is protective in TAC? However, there are a couple of publications from Zumo's lab, as well as Ken Walsh's lab, where they kind of notice the opposite to show physiological hypertrophy and cardiac dysfunction with AKT. How can you explain your present data?
Yeah, no, absolutely. Hi, Thomas. So good question. I think I'm aware of these studies, and they're really, really high quality studies. However, I don't think there is a general consensus about the role or the crosstalk between IKT and mTOR so far, and the literature is just supporting both sides of the arguments, whether AKT activity can trigger or can stimulate mTOR and vice versa. But what I can tell you is that in different models of heart failure that we looked at and we investigated, we often see the improvement in insulin sensitivity, which is often accompanied with an increase in the activity of AKT, is also associated with decrease in mTOR activity. So the question becomes which isoform of AKT is important to trigger mTOR, and the other important question is what pocket and what residue of mTOR that can be more important than the other pockets and residues. I think this is a really interesting scope for further investigation. I'm just hoping that you didn't get this question for your BCAA paper. It's going to be a difficult one to answer.
Kutuba, sorry, do you mind if I just butt in quickly? I mean,
Yeah.
Has anybody compared the AKT levels in these different experimental conditions? You know, are you inducing different, you know, levels of changes in AKT expression?
Yeah, that's a really good question, Deborah. So in terms of the mitochondrial translocation in this experiment that I showed, when we stimulate these hearts with insulin, we see an accumulation of AKT inside the mitochondria. So the answer is yes, we see an increase in the accumulation of AKT inside the mitochondria. And we see that this accumulation following insulin stimulation is impaired in the failing heart. So that was the main conclusion from the last study that I showed you. We think that this impairment in mitochondrial classification of AKT into the mitochondria is what playing a major role in impaired insulin-stimulated glucose oxidation in the failing heart. So yeah.
Okay. But you have no evidence of kind of differences in expression, really, or you can't speculate on that, really, can you?
For different isoforms of AKT?
Well, I mean, for different, you know, different models that have been used, like overexpressing models.
No, that is other people work. No, I'm not aware that this was investigated.
I'm just thinking in light of contrasting conclusions, you know, whether that's explanation.
I think that's a really good idea. No, I agree.
Great, thank you. So the next question I'm seeing is for Dr. Zhao Wang. It's from James, who says, very nice work. Have you observed any association between mTOR change by HBP pathway associated and cardiac autophagy?
That's a very important question. We did try to address this by looking at LC3, for example, Western blot. In our hands, we did not see very obvious change, like a very consistent change from experiment to experiment. So we, you know, to be honest, we don't know the answer, but I guess that's very logical to ask whether activate of mTOR might suppress autophagy in this process. One possibility would be at different stage of the whole process, the answer might be different. But from short answer is we do not know. We don't have a conclusive answer right now.
This is a follow-up question from Bitswani to Kutuba again. I think you answered the GLUT4 part, but do you think GLUT1 somehow get regulated with your inhibitors?
In terms of GLUT1 with the inhibitors, we didn't see much of a difference in the expression of GLUT4 within this short period of time. But we know from molecular glycolysis is that there was no significant difference in glucose uptake. Otherwise, that will drive glycolysis to increase. So I kind of touched on that very briefly. I'm sorry because of the time, but we don't think we had any significant difference in neither glucose uptake or the pyruvate supply to the mitochondria, as evident by no change in glycolysis, which is the main control here.
Thank you. So the next question I'm seeing is for Dr. O'Shea from June Hui, who asks, does oxy-deoxy myoglobin affect optical mapping since it will change the absorbance of myocardium?
Yeah, so the answer is yes. So traditionally, the most commonly used dyes within the field have been excited around 530, and then your emissions look at 630 onwards. So that's right in the sort of in the optical window where you have high absorbance by biological chromophores, in particular oxydeoxyhemoglobin. So what we've seen recently, and what's very exciting, is the production of dyes which are moved forward to infrared and near infrared spectrum. And why it's important is that it allows them for the possibility of doing optical mapping studies without using crystalloid solutions like Krebs solution and so on, but in actually blood perfused systems, and there's not a work that. The answer to that question is, with the dyes that are most commonly used, and even with those near infrared dyes, there will be some change. The answer is yes.
Okay, so the next question is from Rushita to Kutuba. She's wondering, are the underlying mechanism for insulin-stimulated mitoglucose oxidation versus enhancement of glucose uptake and glycolysis mutually exclusive, or is there a crossover between these processes in healthy versus the diseased myocardium?
Hi, Sheta. Good to see you again virtually. Good question as usual. So that's really important to explain. That what we think happening is that these two pathways, whether the direct enhancement of glucose uptake and glycolysis, and thereby feeding more pyruvate into the mitochondria, is working in parallel with the direct insulin stimulation of glucose oxidation in the normal heart. What happens in heart failure is, as I explained in the introduction, we have this uncoupling between glycolysis, which goes up in heart failure, while glucose oxidation is down as an overall mitochondrial oxidative metabolism goes down in heart failure. So we think that we're losing the other part of the metabolic effect of insulin on cardiac energy metabolism, which is the direct effect on stimulating glucose oxidation. So to answer your questions, yes, those are two pathways working together in the normal heart, and we're losing the mitochondrial part, or the direct stimulation of mitochondrial glucose oxidation in the failing heart. And that's what we're trying to restore.
Great. The next question that I see is from Oscar Moreno, who's asking Chris, are you using LED or pulse laser for the stimulation of dyes? Also, I wanted to ask have you noticed a high variability in atrial action potential duration, and how did you manage the problem of spatial averaging of the signals?
Yeah, so to answer the first question, we use LEDs in our specific setups, but other groups also use pulse laser technologies. I think those kind of technologies come more in play when you're looking at more, say, dual dye experiments. We need that fine temporal control, or for example, optogenetic experiments where you have that interplay. The kind of experiments that we've done, it doesn't really, LED illumination works fine. In terms of the atrial preparations, we do see high variability in signal quality mainly. So I'd say it's probably linked to that, where you might get changes in action potential duration. I don't see a huge difference in action potential durations. The quality of atrial preparations in terms of signal you get tends to be less, just for the very simple idea that you have less tissue degradation, less signal quality. You also have sort of thinner tissue and so on. And then, so the third bit about spatial averaging of the signals, again, yes, obviously if you spatial average, you get the blurring of the signals and so on, which obviously isn't advantageous. Sometimes it's necessary just because of poor quality signals. In general, try and avoid these problems, either avoid spatial averaging, or what we try to do is more, when we do apply spatial averaging, apply sort of Gaussian filter averaging, so you get that sort of very sort of fine control, hopefully get rid of the random noise. But yes, that is an issue with optical mapping. Obviously, we try and get these high resolutions. Ideally in the world, we'll never do spatial averaging, but it's again one of these interplays between better quality versus actually then sort of being relevant to the actual signal we get on the line.
Chris, do you mind if I just butt in quickly and just ask a kind of a follow-up question to that? In your opinion, have you ever seen completely different interpretation of the same data set based on, you know, different sort of processing of the data?
Yeah, so obviously if you get a massive underlying change, it will be, even if you apply Gaussian field, don't apply field, it'll still be there. I think the area we've seen it mostly would be when we looked at sort of change through the upstroke. So we did that study with James, where we looked at carbon oxide and fleconide, which are known to have change. And what we did within that study is actually look at different temporal and spatial filters. And what you can see is then, these are very subtle changes, but when you applied some filtering methods, you can no longer see these changes. So yes, I think you can. You can have effects where particularly temporal filtering, I find, if you apply the wrong temporal filter, you can really sort of mask the actual physiological changes or the underlying physiological baseline conditions.
So considering then you are releasing, and Igor Efimov is releasing, you know, software for analysis, do you think now in the papers we need to specify in our results sections or in our method sections what filtering we've used, not only what software have we used?
Oh yeah, well, I think most people, well, what I see, most people do, and they definitely should. I think, yeah, because even if it's just in the supplement, it's definitely a very important factor. In particular, if it's up to the mapping figure, if you get these raw signals, ideally, I'd like to see raw signals all the time as well. But.
Fine. Thank you.
Thank you, Chris. I think now we kind of catch up with Sarah. If I miss your question, I sincerely apologize in between, but the next question is from Kevin Tukutuba. How does the translocation of phospho-AKT occur? In the heart disease, do you have more translocation issue or AKT activity?
Yeah, that's a really good question. I'm not sure if I have the data to support what I'm going to say, but here's what happens. So we see that this translocation of AKT is impaired in the failing heart. I'm guessing you're asking how this translocation actually happens in the normal heart. That's a really interesting topic that we are trying to look at. I have zero data to do any speculation, so I don't know, but it's a fantastic question. Thank you.
Thanks. The next question is from Rio. It's to Katuba and Zhao. It is asking, they're asking a more general question. How does glucose transport from the circulation to the cardiomyocyte? Is it uptaken first by endothelial cells and then pass to the cardiomyocyte, or does it go directly to the cardiomyocytes?
Do you want to have a go, Zhao?
Well, I actually not familiar with this. I think, from my understanding, it's to go through the lymph system. I could be wrong.
I'm curious to hear both of your answers here. I don't know.
It's an important question.
That's better than what I was supposed to. Okay, so here, I can't comment on what happens at the level of the heart, maybe. So we know that insulin can stimulate glucose uptake by stimulating the translocation of GLUT4, and that's why GLUT4 is called the insulin responsive glucose transporter. But the heart can also take up glucose through GLUT1, which is not insulin dependent in an insulin independent manner. So these are the two main glucose transporter into the heart. don't ask me what regulates GLUT1 because I don't know. That's what I know about the uptake of glucose into the heart. I hope that answers your question.
This is like a PhD exam question.
Yeah.
I like to find out what the answer is.
That's a good, but no, absolutely valid question. I like it.
Yeah, it's a good question. I think we have in Purpose Lab, in Philip Shearer's lab, there's a person working on the lymph system. It seems there's a lot unexplored question there right there, how the nutrients or hormones from the circulation get into the targeting cells. The short answer is I'm not entirely sure about this. I need to work on those.
Okay, so I have a couple of questions for Chris from the same attendee. And so this person is wondering, there are multiple fluorescent dyes which can able to measure metabolic changes. Is it possible to use the combination of voltage or calcium imaging and metabolic imaging in cardiac tissue, number one? Second question that this person has is, can your software process dual voltage and calcium imaging?
Yeah, so the answer to the first question is yes. So some of the very earliest optical map experiments actually employed this exact sort of methodology, using metabolic dyes changes with combining them with voltage imaging and so on. I have to say I'm not up to speed with the sort of properties of metabolic dyes, but again, the main problem will be, as with when you try to combine optical mapping with object data techniques, with a spectral overlap problem, the idea that can we effectively separate those two signals? But the answer in theory is definitely yes, and it has been done. The second question, we're working on it. It's getting there. It's kind of thing that's been very stop-start for quite a while now. So we have sort of versions that work and in principle, everything's there. So you can do it manually within our software at the moment. So basically, analyze a voltage signal independently, measure, produce the calcium maps as well, and then sort of interplay them with the raw data. But obviously, it's a very elegant solution, and we are working on making it so there will be a specific module which takes those two channels and combines the data. And then also, hopefully, then if we also do for other dyes, for example, metabolic change and so on. So it's definitely getting there, work in progress. But the answer is kind of at the moment, which is the best answer.
But Chris, this is a really excellent question, actually. And I think we should try this sometimes when we get a chance.
Yeah, I agree.
Induce ischemia locally, see what happens with calcium, as well as, I don't know, like maybe some sort of mitochondrial, fluorescent dye, which will report on mitochondrial activity or something like that. I think.
Yeah, not discovered to do. Yeah, and I think it'd be a great idea. And I think in theory it's definitely possible, and I've seen it done before. So you have to read through and go. Obviously, these things often are quite hard to read to yourselves. So we'll work out. But yeah.
Great. The next question is also for you, Dr. O'Shea, from She. They ask, what do you think is the technique limitation for achieving perfect detection of both calcium and APD signal in mouse heart?
Yeah, so there's a few different things going on here. So firstly is just how the dyes interact with each other would be a simple thing. So one of the things that we found is that in preparations, you get really nice loading of action potential dyes individually, really nice calcium dyes individually. Occasionally when you try to combine them both together, we lose one of the signals for various reasons. We think maybe the saturation with the calcium dye to get the signal, or the sort of interplay. The other things which come from a more technical side are, from the software side, it's not too big an issue. As long as you can effectively separate the two systems, either by the wavelength or another method, for example, dual excitation, then it's pretty simple. Just take the singles, treat them independently, and put them together at the end. What's more of an issue, and again, we ourselves haven't done many experiments, but from speaking to other people who have, seems to be the hardware problem, getting that perfect alignment between the tissue. So you know that one pixel in your voltage image is exactly the same as your pixel in your calcium image. And that seems to be an issue for quite a few people. So that's one of the other sort of technical limitation. But again, it's routinely possible, and there's many groups that do it. So it's definitely possible.
Okay, so the next question, based on the question, I think it is for you, Chris. I'm going to tag the follow-up question to the next question together. So if you can answer both at the same time, that would be great. So can you use your technique, optical mapping, in vivo? That's the first question. I think the same attendees are wondering, do you think more than 2 cameras will reduce the distortion of imaging?
Yeah. So the first question, it's getting there. So originally it was, so quite a few of the different things I talked about, for example, need for mechanical uncoupling, the problem with toxic dyes and so on, has traditionally limited to be an ex vivo technique, but there's been some really nice work, well, actually quite a while ago, sort of using strategies such as pulmonary bypass to achieve this sort of more in situ optical mapping. There's been recent work that's combined some of the motion artifact correction techniques with some of the sort of those redshifted dyes that I mentioned, which have achieved these almost, you could say, in situ, well, in vivo optical mapping using fiber array detectors. Particularly Peter Lee has produced quite a lot of really nice work recently on this subject. So it's getting there. It's not sort of as high resolution, for example, to electrical mouse heart, but it is getting there. Will we ever get to the point where it can be clinically relevant? There is sort of 1 or 2 FDA approved optical voltage dyes and so on, but that's a long, long way still away from actually becoming possible. For the second question, so it depends what sort of distortion the attendees actually thinking about in terms of mechanical coupling. So if you have a heart that's still beating, it could help slightly because you get those two camera views, so you can see which way the heart's moving. Then you can apply these motion, these computer vision techniques. If you talk about distortion just in terms of other artifacts, for example, things like optical blurring and so on, what you need to do really in terms of sort of the 3D architecture is combine sort of surface capture software as well. Our algorithms actually very detailed to capture software. So having more cameras does help that and make that easier, but it's still not a trivial problem. And in particular, Eagle FMOS group has, well, about a couple of years ago now, to release sort of suite of open source software platforms for this exact reason, because it's really hard computational problem, even with 4 cameras. So I look at each view. To combine them all together and get true 3D optical mapping is still pretty difficult.
Thank you. The next question is for Dr. Wang from OSMA. They ask, did you check some common readouts of autophagy like LC3 and Becklin-1?
Oh, yeah, I mean, he also followed up with that. We did, like the question I addressed previously, we look at LC3. We didn't look at a Becklin-1, but LC3, as I said, we don't have a very consistent and convincing change across different experiments. So, so we think a short answer is we don't think it's strongly changed it.
Okay, in my screen, I don't see any more questions. So let's, Sarah and I, thank you.
Sorry, there's one more question in the chat from what I can see.
Oh.
Can you see it from Wahiba Dari?
Chat. Can you please ask? Because I was chatting too much.
I do see it. So it sounds like it's for Dr. O'Shea. They say, I'm using optical mapping to image synchronously engrafted cardiomyocytes expressing autonomous voltage sensors with the guinea pig host myocardium dilated. If activation map analysis is done separately for each channel, would it be possible to combine data from both to see if the graft is coupled or not?
Yeah, so I believe so, yes. You'd have to, the problem with combining different channels like that is if you have a defective reference, then to basically to stitch those signals together. I believe, yes, without sort of seeing the actual intricacies of this experiment, it sounds like a very complicated setup, you're not going there, but I don't see why that shouldn't be possible.
But that should be probably the same issue like the voltage calcium,
yeah,
right?
Exactly. As long as you have an appropriate reference, for example, I don't know how you're stimulating these preparations, but if you have something to reference, so you can make sure. One of the problems if you analyze 2 things separately, and for example, our software, which is you're basically looking at the actual intrinsic signal within, for example, the optical voltage signal as a time reference. But so then we're doing that separately with 2 different channels. You need to make sure there's a common channel or common stimulus in both channels where you can effectively line things. So that would be the only sort of limiting factor in doing that. But that should be routinely possible from what you say.
But Wahiba, I mean, I would just say that you may want to just contact Chris. I don't know if Chris, you have time, but you know, he may be able to help, because I know that Chris, you've dealt with a few issues like that so far, but similar.
We've always found a way around it. So.
Okay, same goes to every other questions. If you want to email Kutuba or Zhao directly, please ask your question. I don't think any more question at this time. So Sarah may conclude the session.
Thank you again for everyone that spoke today, and for those that attended and asked questions. We're grateful for everyone's contribution today, and just wanted to again thank everyone and remind you these are a continuing series to join in for another time. Thank you.
Thank you very much for taking care of us. And
Thank you.
Everything. Thanks
You
a
guys,
lot.
well done. Great talk.
Good to see you guys.
Thank you.
Bye-bye.
Bye. Bye, everyone.
Bye-bye. Thank you.
Bye-bye.